Okay, let's continue. We have already talked about the central limit theorem, and we have already know if we draw samples from a population with sample size of n, and we can get x bar, and we already know that x bar follows a normal distribution with mu and sigma square over n, and we said that x bar is symmetric about mu, which is the population mean of the original data, and the standard deviation of x bar, actually we can call it standard error of the mean, denoted by sigma x bar, and sigma x bar equals to sigma over square root n. So according to the central limit theorem, we can know some results, which is very important. The first one, the mean of the sampling distribution of x bar, denoted mu x bar, is equal to mu, the mean of the population. We have just explained what's the meaning of this point, and we said that x bar is symmetric about mu. If we use mu x bar to represent mean of x bar, we use mu x bar to represent the mean of x bar, we will find that mu x bar is equal to mu. So that is the same with what we explained, that x bar is symmetric about mu. So they are the same. So this is the first result we can get from the central limit theorem. And the second one is the variance of the sampling distribution of x bar, denoted sigma x bar square, equals the variance of the population divided by n. So that is actually the formula of variance of x bar. We said that we use sigma x bar to represent the standard error of the mean, and sigma x bar square means the variance of x bar. So the variance of x bar equals to sigma square, which is the variance of the original data divided by the sample size, little n. And we said that the standard error of the mean, denoted by sigma x bar, equals to sigma over square root n. So this one we can call it standard error. So the standard error of the mean is the standard deviation of the sampling distribution of sample means. So that is very special. So you need to distinguish the difference between standard error and standard deviation. When we are talking about the standard deviation, actually we mean sigma, and we said that standard deviation is sigma. So this one, sigma or standard deviation, means the standard deviation of the original data, for example x. But sigma x bar, we can call it standard error. Actually, this is the standard deviation of x bar. So we give it another name, standard error. So you need to know that when we are talking about the standard deviation of the original data, for example x, we can use sigma to represent this value. But when we are talking about the standard deviation of x bar, which is the sample mean, it must be sigma x bar, and we give it another name, that is standard error. So they are not the same, and we can find they have some special relationship between sigma and sigma x bar. The relationship is the formula. So we can use sigma and the sample size little n to calculate the standard error sigma x bar. Okay, so the last result which we can get from the central limit theorem is the sampling distribution of sample means is approximately normally distribution regardless of the shape of the population. So that means no matter the population follows a normal distribution or not, when we are drawing samples from this population, and then we can get some different samples, we will find that the mean of the samples still follow a normal distribution. So those are the results what we can get from the central limit theorem. So that is very important. Okay, next one, let's try to prove the central limit theorem. Actually, we have already proved something about the theorem. That is mu, or we can say x bar is symmetric about mu. And we have mentioned that if we have 4 numbers in a population, we use x to represent any number of the population, and x can be equal to 0, 1, 2, or 3. When we choose 2 numbers from the population, and we can get 2 numbers, we consider these 2 numbers as a sample, and then we can calculate the sample mean x bar. So we will find that x bar is symmetric about mu, the population mean, and the population mean equals to 0 plus 1 plus 2 plus 3 divided by 4, and mu is 1.5. We have already proved this one. And next one, how about sigma or sigma square? We can use some special formula to figure out the sigma square, namely the variance. For example, here for the population of the 4 numbers, we can figure out the sigma square. The sigma square is 1.25, and then we will find that sigma square divided by n equals to 0.625. So this is the value of sigma square divided by sample size. And then let's try to figure out the sigma x bar square. The first thing is to figure out the mean of x bar. We use mu x bar to represent the mean of x bar, and we have mentioned that mu x bar equals to mu, so the number should be 1.5. That is what we can get from the central limit theorem. And next one, how about sigma x bar square? We still use the same formula to get the value, and we will find that sigma x bar square equals to 0.625 is exactly equals to sigma square over n. So that means sigma x bar square equals to sigma square divided by n. So that is how can we get the formula for variance of sigma of x bar. Okay, so here when we know the formula of sigma x bar, we can use the formula to solve some special questions. For example, here consider a normal population with mu equals to 70 and sigma square equals to 25. If a sample of size 16 is randomly selected from this population, what is the standard error of the mean? So here, let's analyze this question. The first thing which is given, that is mu equals to 70. So here we can find that this is mu, so that means this number 70 is a population mean. And the next one we can find here sigma square, so this is the variance. We said that sigma square is variance. Variance equals to 25, and we can find that sigma, that means this is the variance of the population. And next one we can find that in this question the researcher randomly drew samples from the population with the sample size of 16. So 16 is actually sample size, the little n. So that means n equals to 16. Okay, so here the question is, what is the standard error of the mean? So according to the center limit theorem, we can know that standard error of the mean is sigma x bar, and according to the theorem we have already know that it equals to sigma divided by square root n. Here we can know that sigma square is given, and we can figure out the sigma. When sigma square equals to 25, that means sigma equals to 5. And next one, the little n is 16. So we have already know these two numbers. We just put these two numbers into the formula, and then we can get the answer to this question. So here we can find that mu, this value of population mean, is useless. It's not useful in this question. Okay, so here this is another question. It's more complex. So we can find that it has the same information but different question. What is the probability that this sample will have a mean value between 68 and 72? Okay, so here let's think about it. The question is the probability of the sample have a mean between two numbers. So here we can find that the sample mean, that means x bar. So it means we need to know the probability when x bar is between these two numbers. So that means what is the probability when x bar is more than 68 and less than 72? So how can we solve this question? We want to know something about the probability. So do you remember that in chapter 2 we have already learned some special probability? It's based on a standard normal distribution. So that means it follows a z distribution. So if we can change x into z value, we can use table A1 to get the probability for this z value. So here, this is the same thing. We said that z distribution is a special normal distribution. So here, in this question, what we are talking about is not x, but x bar. So we can use the same method. We transform x bar into z value, and then we can still use standard normal distribution to get its corresponding probability. So here in chapter 2 we have mentioned that if we want to figure out the z value, the formula should be like this: x minus mean of x divided by standard deviation of x. But here we have mentioned that this is not x anymore. We need to transform this one into x bar. So we need to replace all the x with x bar. So this one should be x minus mean of x bar. The mean of x bar is actually mu x bar, right? And we have already known that mu x bar is actually mu. They are the same, they are equal. And next one, standard deviation of x bar, not x. And we said that standard deviation of x bar is actually standard error of the mean. It should be coded as standard error of x bar, standard error of sample mean. So this one should be sigma x bar. And we also know that sigma x bar equals to sigma divided by little n. Okay, so next one, let's go back to the question. Let's find all the values which we need. The first one, mu. We can find it here. Mu equals to 70. And next one, sigma. In this question, we don't know sigma, but we know sigma square, right? Sigma square equals to 25, so sigma equals to 5. And the next one, sample size. The little n equals to 16. So we have already know 1, 2, 3 numbers. But how about the other one? The last one, the last value is x bar. We need to know the value of x bar, and then we can figure out the z value. So how can we get x bar? Do you remember that the question is the probability when x bar is between two numbers. So we have another two numbers, 68 and 72. So we can use either one of the true to represent x bar. So that means we can get two z values. The first z value is calculated when x bar equals to 68, and the second z value should be calculated when x bar equals to 72. Okay, so here we put all the numbers into the formula. This is the first one when x bar equals to 68, and this is the second one when x bar equals to 72. We can get two z value, and we find that the first z value is negative 1.6, and the second one is 1.6, a positive number. So actually in that question we want to know when x bar is bigger than 68, less than 72, but here we use the formula of z value. Actually we transform x bar into z value, and we also transform these two values, these two numbers 68 and 72, into two z value. The first one is negative 1.6 and the second one is positive 1.6. So that means now we want to know the probability when z is between these two values, right? Okay, so how can we know the probability? I think we have already learned that in chapter 6. So the first one, we need to check the probability for each value of z in table A1. Okay, so let's turn to our table A1. Okay, we can find that this is table A1. This is the cumulative distribution function for standard normal distribution. And here we have mentioned that we need to find the z value, and here the z value is negative 1.6, so we need to find out this number in the first column here, negative 1.6, and we need to find the second number after the dot. Actually this number should be negative 1.60, so we can find that 0 is here, and in the cross position this number is the probability when z equals to negative 1.6. Okay, so here let's go back to the distribution curve. That means when z is negative 1.6, this blue part, the area of this blue part is 0.0548, and in that question what we want to know is the probability between negative and positive 1.6, this right part. And according to the property of normal distribution, we can know that the total area and the curve is 1, and the curve is symmetric about z equals to 0. So that means in the left way, the blue part, the area of the blue part is 0.0548, in the right side, this part should have the same area. So that means between these two values, its probability should be 1 minus 0.0548 times 2. That means the part except the left blue part and the right red part and this part in the middle. So that is the answer to this question. We can find that the probability is 0.8904. Okay, so this is how can we use the formula of sigma x bar. Next one, let's talk about the concepts of hypothesis test. In chapter 4, we only need to know some basic concepts, some basic definitions about hypothesis test. In chapter 5, 6, 7, 8, we are going to learn some methods of hypothesis test. I will show you some more details about the hypothesis test. So in chapter 4, it's only an instruction for the hypothesis test. So often, a researcher is interested in comparing his data against some numerical standard. This standard may be based on values from previous study or be an attempt to compare several methodologies or drugs. In statistics, we make comparisons of this type by testing a stated hypothesis. A hypothesis is a statement that something is true. We then want to make a decision as to whether the stated hypothesis is reasonable in light of the data that is subsequently collected. So that means this method of hypothesis testing is used for comparing. For example, we want to know the effect of two drugs. We want to know which one is better, so we need to compare the effect of these two drugs. But we have mentioned that in most of the research, what we can do is sampling study. So that means we cannot get the population. We can just do the research in a special sample, not the population. So sample is different from the population. So if we can prove drug A is better than drug B with the data of two samples, so how about the population? We have already know that sample is different from the population. So although we have already know sample A is better than sample B, but the underlying population is unknown. So we cannot still know the difference between the two populations. So at this moment, we need the method of hypothesis test. So hypothesis testing is to make a decision as to whether the stated hypothesis is reasonable to compare our data against others or against some numerical standard. So let's take an example. Let's consider an artificial example to illustrate the basic ideas of hypothesis testing. So, suppose you meet an acquaintance on the street and he proposes that you play a game of chance with him. He then produces a coin from his pocket. Suspecting that something may be wrong with the coin, he allows you to inspect it and try it. We decide to toss the coin 10 times and then decide to play or not play depending on the outcome. We then are prepared to perform the first step of the hypothesis test procedure. Formulate the statistical hypothesis to be tested. Actually, we formulate two hypotheses: the null hypothesis and the alternative hypothesis, that correspond to the choice of the two decisions that must be made. The null hypothesis, denoted H0, is that the coin is fire, and the alternative hypothesis, denoted HA, is that the coin is not fire. The null hypothesis is established as a status quo statement. For example, the coin is assumed fire until shown by the sample data to be unreasonable. So here, if we let x be the number of heads in 10 tosses of the coin, we have already known that for a coin, it has two sides, head and tail. So we use the x to represent the number of heads, and we need to toss the coin for 10 times. So we use x to be the number of heads in 10 tosses. If we assume independence between tosses, then x is a binomial random variable. So the real question of concern is, what is the value of theta? We use theta as the probability of obtaining a head. So notice that theta means the probability. The probability of obtaining a head in one toss. So here, if the null hypothesis is true, do you remember what is the null hypothesis? We said that we use H0 to represent the null hypothesis, and H0 is the coin is fire. So let's think about it. If the coin is fire, what is theta? That means if the coin is fire in one toss, what is the probability of obtaining a head? Yes. If the null hypothesis is true, theta should be equal to 0.5, right? Because the coin has only two sides. So if the coin is fire, theta must be 0.5. So this now brings us to the second step of hypothesis testing, determining if the null hypothesis is reasonable or not. So that means we need to make decision that the null hypothesis is right or wrong, or we can say that if the coin is fired or not. So in this step, actually what we need to do is try to prove the null hypothesis should be refused. So we need to find something to refuse the null hypothesis. We try to prove that. To do this, we must set up a decided plan for making a decision. To make up this plan, we must first look at the probabilities associated with each value of calculated with formula in section 3.4.6 with n equals to 10 and theta equals to 0.5. So here we list all the possible value of x and its corresponding probability in this table. So let's think about this question. We said that x means the number of heads in 10 toes. So what are the possible values for x? So that means if we toss the coin for 10 times, maybe we can get 10 tails, right? So it's very unlucky, right? There is no heads in 10 toes. We get a tail, and then a tail, and then a tail, and again and again, until that we can get 10 tails. So at this time, x equals to 0 because we got no heads in 10 toes. And next one, maybe we can get only one head and the rest are all tails, right? Okay, and maybe we can get 2 heads and 8 tails, so x can equal to 2, and so on. We can find that x can be any number between 0 to 10, and then we can calculate its corresponding probability, right? So let's think about this question. So for example, this one, when x equals to 1, what is the probability? Maybe this question is a bit difficult for you, so let's change another number. When x equals to 0, what is the probability? So x equals to 0, that means in 10 toes we had 10 tails. So let's think about the probability for a tail in 1 toes. We said that theta is the probability for a head in 1 toes, and it equals to 0.5. So that means if we get a tail in 1 toes, the probability should be 1 minus theta. So it still equals to 0.5, right? Okay, so here in 10 toes we get 10 tails. The probability for these 10 tails should be 0.5 times 0.5 times 0.5 times 0.5. We need 10 0.5, right? So it's the product of 10 0.5. So the probability is 0.001. So that is the probability when x equals to 0. Okay, so next one, when x equals to 2, when x equals to 1. So x equals to 1, that means in 10 tosses we had only 1 head and 9 tails. So what is the probability? Maybe some of you will think that the probability is the same, right? 0.5 multiple 0.5 times 0.5, right? But it's a little different, because we said that x equals to 1. There is only 1 head in 10 tosses, but we don't know the sequence. So that means in 10 tosses, maybe the first one is head and then 9 tail, and maybe the first one is tail, the second one is head, and the rest are tails. And there is another condition, that is 2 tail and the third one is head, and so on, right? So how many possible conditions can we get? Yes, we can get 10 possible conditions. So the probability of when x equals to 1 should be times by 10. So that means 0.5 times 0.5 times 0.5 and so on, and finally times 10, because we have 10 possible conditions. So here the probability should be 0.0098. So that is the probability for x equals to 1. And how about x equals to 2? That's more confused, right? Okay, so here you can try to prove that after the class. So here I just list all the value of probability here in this table. Okay, so here when x equals to each number, we can figure out its corresponding probability. And here, according to the results shown in this table, we can find that if the coin is fire, then 5 heads is the most likely result, right? We said that we figure out the probability, which is based on sigma equals to 0.5. That means we assume the coin is fire, and then we can find that this number, this is the biggest probability. That is when x equals to 5, but it's based on sigma equals to 0.5. So that means if the coin is fire, then 5 heads is the most likely result. But this result only occurs when probability 0.2461. Thus, it would be unreasonable to decide to play if we only obtain exactly 5 heads, since other values, such 4 or 6 heads, are also quite likely, because we can find here when x equals to 4 or x equals to 6, the probability is closer to this one, right? So that means even if the coin is really fire, we can still get 4 or 6 heads in 10 tosses, because they almost have the same probability. In fact, it's possible to obtain any value of x with a fire coin. For example, if the coin is fire, but we are so unlucky, we can still get 0 heads but 10 tails. So I can just say you are so unlucky, but the coin is fire, right? But we can find that the probability of this condition is too small. So you can start to see the problem that we face with hypothesis testing. Anything is possible, but certain value of x arouse our suspicions. That is, it's possible to obtain a value of x equals to 1 even when a fire coin, but it's not likely because the probability is too small. Thus, in hypothesis testing, we must make our decision on what seems most reasonable, realizing that we must of necessity take a risk of making an incorrect decision. So that is what we need to do in hypothesis testing. Okay, so this is the basic concept of hypothesis testing. Next one, hypothesis testing, that doesn't mean the conclusion of the hypothesis testing must be correct. We can still make some wrong decision based on hypothesis testing. So there are actually 2 types of incorrect decisions or errors that can be made in this context. These 2 errors, which is called type 1 error and type 2 error. So what's the meaning of type 1 and type 2 error? Please notice that the type 1 error occurs when an error is involved with a true H0. The type 2 error is involved when the H0 is false. So that means if the coin is really fire, then we should not reject H0. But in 10 tosses, we obtain 2 heads or even less. Then we reject H0 based on our result of 10 tosses, right? Because we believe that if the coin is fire, we should get 4, 5, or 6 heads. It's not possible for us to get only 2 heads. So we believe that the coin is not fire, so we reject the H0. But actually H0 is true. But we do know that, right? We do know the truth. We just make a decision based on what we can see in this study. So we make a wrong decision. So here we make a type 1 error. So what's the meaning of type 2 error? If the coin is not really fire, so that means H0 should be rejected. But by chance, in 10 tosses, we can still get 5 heads. And at this time, Although the coin is not fired, but we don't know that. What we can know is only we get 5 heads in 10 tosses. So we believe what we can see in this study. And we believe that, oh, the coin is fired because we get 5 heads in 10 tosses. So we don't reject the H0. But actually, H0 should be rejected. We just don't do that because we make the decision based on what we saw, what we see, or what we saw in the study. So at this time, at this moment, we make a type 2 error. So what is the probability for type 1 and type 2 error? We will talk about this question next class. Okay, so today's class is over.